We spend a lot of time on this show talking about how smart artificial intelligence is. We talk about neural networks, deep learning, these systems that seem to know everything.
Mm.
But I was reading through the research for today's deep dive, and I realized we rarely talk about what happens when an AI, well, when it doesn't know.
Which is, I mean, that's actually most of the time.
Right. We assume AI is this creature of pure cold logic, true or false, one or zero.
Yeah.
But the stack of notes we have today is arguing that logic, old school strict logic, is actually terrible at navigating the real world.
It is. It really is. If you try to build a robot using only strict logic, it's going to have a nervous breakdown the moment it steps out the door.
Right.
Today is really about how AI learned to stop worrying and love the gamble. We're talking about uncertainty.
And to set the stage, I want to look at this scenario from the source material called Plan A90. It sounds like a secret military operation or something.
It does.
But it's actually just driving to the airport.
It's the classic airport problem.
So, the setup is simple. You're an intelligent agent, maybe an automated taxi. You have a goal: get the passenger to the airport to catch a flight. You come up with Plan A90, leave 90 minutes early, and drive at a reasonable speed.
Okay.
Now, a logical agent needs to know, is this plan true? Will it succeed?
And this is where the trouble starts. I mean, in strict logic, for a rule to be valid, it has to be universal. So the agent tries to reason, if I leave 90 minutes early, I will arrive on time.
But that's just not true.
No, it's not. So the agent has to add a qualification. I will arrive on time unless the car breaks down.
Okay, that seems reasonable.
But is it true yet? No, because what if you run out of gas?
Okay. I will arrive on time unless the car breaks down and unless I run out of gas.
What if there's a bridge collapse? What if a plane lands on the highway? What if you get arrested?
What if a meteorite hits the taxi?
Exactly. And this is called the qualification problem. To make that sentence logically true, with 100% certainty, you have to list every single unless condition.
And in the real world, that list is...
It's effectively infinite.
So the AI is just stuck. It can't prove the plan will work, so it just sits in the driveway, buffering, trying to list every potential disaster in the universe before it puts the car in gear.
It's the paralysis of analysis. Logic demands certainty, but the real world refuses to give it. If you wait for 100% certainty, you never act. You miss the flight every single time.
So the source material breaks this down into 3 specific reasons why logic fails here. And I love the first one because it feels so human. Laziness.
It does sound funny, but in computer science, laziness is often a virtue. It's really about efficiency.
Right.
Even if you could list all the exceptions, which you can't, it's just too much work. It is computationally lazy to avoid checking for meteorites every time you want to go to the grocery store.
Yeah.
It's a waste of processing power.
So we have laziness. What are the other 2?
The next is theoretical ignorance. This is when we just don't have a complete theory of the domain. Medical science is the perfect example here.
Okay.
We understand a lot about the body, but we don't have a complete theory. We can't predict exactly how a specific drug will affect a specific person because, science isn't finished yet.
We don't know what we don't know.
Exactly. And the third is practical ignorance. This is even more common. Even if we knew all the rules perfectly, let's say we had a perfect theory of cars, the AI taxi doesn't have the data for this specific car right now.
It doesn't have a camera inside the transmission.
Right. It might know that worn gears cause breakdowns, but it is practically ignorant of whether these gears are worn.
So because of laziness, theoretical ignorance, and practical ignorance, the AI has to give up on true-false. It has to switch to a different language entirely.
The language of probability.
Which feels like a surrender, doesn't it? It's like the AI is saying, I don't know for sure, so I'm just going to guess.
But it's not a guess, though. It's a degree of belief. It's a rigorous way of managing that ignorance.
Yeah.
The source uses the dentist example to show this shift.
Right, the toothache rule.
So in logic, you might try to write a rule. Toothache implies cavity. If the agent sees a toothache, it concludes cavity.
But that's wrong. I could have a gum infection. I could have bitten a popcorn kernel. I could have an abscess.
So the logical agent tries to patch it. Toothache implies cavity or gum disease or abscess, and we are right back to that infinite list.
So the probabilistic agent just looks at the data and says, what?
It says, the probability of a cavity given a toothache is 0.8. Or, 80%.
And this is the part that I think is really important to nail down. When the AI says 80%, it's not talking about the tooth, is it?
No, and this is a huge stumbling block for people. In the real world, The tooth either has a hole in it or it doesn't. The probability is 1 or 0. The physics are settled.
So the 80% is just a measure of the AI.
It's a report on the agent's own state of knowledge. It's subjective.
Yeah.
If I look at your tooth and see a hole, my probability updates to 100%. The tooth didn't change. My information did.
I see.
Probability is the technology we use to handle the fact that we are not omniscient.
Okay, so we've established that we can't know anything for sure. We have a degree of belief. I believe there is a 97% chance Plan A90 gets us to the airport.
Right.
But believing isn't doing. Just because something is likely doesn't mean it's the right choice.
Now we are crossing the bridge from inference to decision-making. You can have the best probabilities in the world, but if you don't know what you want, you can't act.
This is where utility comes in.
Correct.
Now, when I hear utility, I think of the power company, or maybe a utility knife. But in AI, this means something really specific.
In decision theory, utility is just a score. It's a number representing how desirable a specific outcome is to the agent. It's a preference ordering.
Is that just a fancy word for happiness?
Roughly, yeah. But it captures more than just joy. It captures trade-offs.
Let's go back to the airport to see how this works. We have Plan A90 leave 90 minutes early. It has a 97% success rate, high probability.
But let's propose Plan A1440.
Leave 40 minutes early, 24 hours.
If you leave 24 hours early, the probability of missing the flight drops to basically 0. Mathematically, it is the safer bet. So if the AI only cared about probability of success, it would choose the 24-hour plan every single time.
But that's a terrible plan. I'd have to sleep on a plastic bench. I'd have to eat overpriced stale bagels for breakfast, lunch, and dinner. The experience would be miserable.
Exactly. So we say that outcome has low utility. A rational agent doesn't just maximize the probability of success, it maximizes expected utility.
MEU, maximum expected utility.
Right. It's an equation. You take the probability of the outcome, you multiply it by the utility of that outcome, and you balance the 97% chance of catching the flight against the cost of waiting in the terminal.
And that explains why we take risks. The utility of not sleeping at the airport outweighs the small risk of missing the plane. But wait, can I just rig the system? Who defines utility? If I build a robot that loves pain-like, its utility function gives a huge score to crashing the car. Is it still rational if it drives me into a wall?
Yes. That's the scary part.
Huh.
Rationality has nothing to do with what you want. It only measures how consistently you act to get what you want. If the agent prefers jalapeno bubblegum ice cream or crashing cars, the rational move is to maximize the probability of getting that result.
So decision theory equals probability theory plus utility theory. That's the formula for a rational agent.
That is the core equation of modern AI.
I want to push back on the probability part of that equation, though. We're acting like probability is this hard rule, but we just said it's subjective. It's a belief.
Right.
So why can't I just make up my own math? Why can't I build an agent that believes rain is 40% likely and no rain is 30% likely, and who cares if it doesn't add up to 100?
You could build that agent. It's just going to go bankrupt.
Go bankrupt.
There is a famous proof from 1931 called De Finetti's theorem. It's also known as the Dutch book argument. It turns philosophy into a gambling problem.
Well, I'm listening.
De Finetti proved that if your internal beliefs don't follow the axioms of probability, like if your percentages don't sum to 1, or you think A and B is more likely than just A,
Okay.
then a competitor can place a series of bets against you where you are guaranteed to lose.
Not just likely to lose.
Guaranteed.
Yeah.
Mathematically. Doesn't matter how the world turns out. It doesn't matter if it rains or shines. If your internal math is inconsistent, there is a combination of bets that forces you to lose money every single time.
So rationality isn't just a nice idea, it's a survival trait.
Exactly. If an AI doesn't follow the rules of probability, it will be exploited by the environment. The math forces you to be rational, or you get wiped out.
Okay, so the agent has to play by the rules. It has its utility scores to know what it wants. Now we need to look at the engine under the hood. How does it actually calculate these beliefs?
Right.
We need to talk about Bayes' rule.
Bayes' rule. It is the fundamental equation for updating belief with evidence. It's how we learn.
And the text uses a medical example, meningitis, that I think really clarifies why we need this formula. It talks about the difference between the diagnostic direction and the causal direction.
This is a huge concept for engineering robust systems. Let's look at meningitis. A classic symptom is a stiff neck.
So if I'm a doctor or a medical AI, I want to know the diagnostic probability, P of meningitis given a stiff neck. If I see the neck, what are the odds of the disease?
That's the number you want. But here's the problem. That number is unstable.
Unstable how?
Imagine there's a sudden epidemic of meningitis. The hospitals are full of it. Suddenly, the probability of meningitis goes way up.
Mm-hmm.
That means if you walk in with a stiff neck today, the probability you have the disease is much higher than it was yesterday.
So if I programmed my AI with a hard rule, stiff neck equals 10% chance of meningitis, my AI is wrong the moment the epidemic starts.
Exactly. You'd have to manually rewrite the code every time the disease prevalence changed. That's just bad engineering.
So Bayes' rule lets us use the causal direction instead.
Right. We look at P of stiff neck given meningitis.
Yeah.
We ask, if a patient has meningitis, how likely are they to get a stiff neck?
And that number doesn't change during an epidemic.
No, that's physiology. The disease causes the symptom about 70% of the time. It doesn't matter if one person is sick or a million people are sick. That causal link is a stable fact about the world.
I see. So Bayes' rule lets the AI store that stable causal fact and then just combine it with the prior, the general read of the disease, to calculate the diagnosis on the fly.
Exactly. If an epidemic starts, you just update one number, the prior, and the AI automatically updates all its diagnoses correctly.
Let's run the actual numbers from the source because they are surprisingly low.
They are. So meningitis is very rare. The prior is 1 in 50,000. Stiff necks, however, are common. About 1% of people have a stiff neck for some reason or another.
And we know meningitis causes a stiff neck 70% of the time.
So when you plug those into Bayes' equation,
You get 0.00014.
about 1 in 700.
That feels wrong, doesn't it? If I have the main symptom of a deadly disease, I feel like the odds should be higher than 1 in 700.
That's because your human brain ignores the prior. You forget how incredibly rare the disease is to begin with. Bayes' rule forces the AI to respect that rarity. It prevents the system from panicking,
It keeps the AI from becoming a hypochondriac.
which is very important if that AI is triaging patients.
Now, Bayes' rule is great for one symptom, but the real world is messy. You usually have a stiff neck and a fever and a toothache, and you just ate bad sushi.
Right.
When you start adding variables, the math gets scary fast.
This leads us to the problem of complexity, and the text illustrates this with the Wumpus world.
I love the Wumpus world. It sounds like a bad 80s arcade game.
It's a classic AI test environment. Imagine a grid, a dark cave. There are deep pits you can fall into. There's a monster, the Wumpus, and you are a robot trying to find gold without dying.
And the catch is, you can't see the map. You only have local sensors. If you stand on a square next to a pit, you feel a breeze.
So imagine the robot moves one square. It feels a breeze. Logic says, okay, there is a pit in one of the adjacent squares, but doesn't know which one.
It's a 50-50 guess between the square to the north and the square to the east.
Now, to figure this out properly, the AI needs to update its belief based on all the evidence, and here is where the computation just explodes. If you want to be perfectly precise, you have to calculate the probability of a pit for every possible combination of squares in the entire cave.
Why? Why does the far corner of the cave matter?
Because in a fully connected probability model, everything could theoretically affect everything else.
Yeah.
If the cave has 100 squares, the number of possible configurations is 2 to the power of 100.
That's a big number.
It's larger than the number of atoms in the observable universe.
Yeah.
If a supercomputer started calculating that at the Big Bang, it wouldn't be finished yet.
So we have a problem. The math works, but we don't have enough time in the universe to compute it. How do we cheat?
We use independence.
Independence is when two things don't affect each other. Like, my toothache doesn't change the weather in London.
Right. Those are absolutely independent. But in the Wumpus world and in the human body, things are connected.
Yeah.
The pit causes the breeze. They aren't independent.
So we can't just ignore the connections.
So we use a more powerful tool, conditional independence.
Yeah.
This is the secret sauce of scalable AI.
Walk me through that. How is it different?
Go back to the dentist. You have a toothache, and the dentist's probe catches in your tooth. Are those two things related?
Yeah. If I have a cavity, I'll probably have both.
Right. They are correlated. If you have a toothache, it's more likely the probe will catch. But, and this is the key, given that we know you have a cavity, the toothache and the catch are independent of each other.
Wait, unpack that.
The cavity causes the pain. The cavity causes the catch. But the pain doesn't cause the catch. And the catch doesn't cause the pain. If I fix the cavity, the link between them is broken. They are conditionally independent given the cause.
So if I know the cause, I can treat the effects as separate problems.
Yes. And that allows us to take that massive 2 to the 100th math problem and break it into tiny little chunks. We can calculate the probability of the pain multiplied by the probability of the catch. It turns a universe-ending calculation into simple multiplication.
Applying this to the Wumpus world, this means the robot doesn't need to worry about the squares on the other side of the map.
Exactly. It can define a frontier, the squares bordering the unknown. It can mathematically prove that the rest of the cave is conditionally independent given the frontier. It can just ignore the rest of the world.
And when you run those numbers, the results are actionable. In the example from the text, the robot is standing near two dark squares. Logic just says, maybe, but the probability engine says, square 1 out of 3 has a 31% chance of a pit. Square 2 out of 2 has an 86% chance.
That is a massive difference.
It's the difference between life and death.
Literally. Logic leaves you paralyzed. Probability gives you a flashlight. It says, don't go to 2 and 2. It's not certainty, but it's enough to survive.
It feels like the theme here is good enough. We aren't trying to be omniscient gods. We're just trying to make it to the airport.
That's the definition of intelligence in AI. It's not about knowing the truth with a capital T. It's about making the best possible bet with the limited information you have.
Before we wrap up, the source mentions one specific model that takes this good enough idea to the extreme. Naive Bayes.
Yes, sometimes affectionately called idiot Bayes by researchers.
That's a harsh nickname. Why idiot?
Because it makes a really, really dumb assumption. It assumes that all effects are conditionally independent.
Which is almost never true in real life.
Right. Take a spam filter. It looks at the word Prince and the word Nigeria. A naive Bayes model assumes those words have nothing to do with each other, except that they both point to spam.
But they are clearly related. They are part of the same sentence structure.
Exactly. The model is wrong. It is naive. But here's the kicker. It works. It works incredibly well. It powered the internet's spam filters for a decade.
Huh.
It turns out that even with a simplified, slightly dumb model, the probabilistic approach is so robust that it still gives you the right answer most of the time.
It's better to be roughly right than perfectly paralyzed.
Perfectly put.
We've covered a lot of ground here, from the infinite unless list that breaks logic, to the betting arguments that force us to be rational, to the Wumpus world.
It's the journey from rigid logic to flexible belief.
And I want to leave the listener with one final thought from the source material. It's a bit of a philosophical curveball. We've been talking about probability this whole time. 80% chance of rain, 30% chance of a pit.
Right.
Is that probability real? Like, does the universe actually roll dice? Or is probability just a mirror of our own ignorance?
The subjective versus objective debate. It's the oldest fight in statistics. The objectivists say probability is a property of the world, like mass or energy. The subjectivists say it's just in your head.
But the source seems to take a pretty strong stance on this, at least regarding AI.
For AI, the debate is irrelevant. And here is why. To the AI, it doesn't matter if the coin flip is truly random physics or if it's just too complicated to calculate. The result is identical. The agent is ignorant.
So because we can never know the full truth,
We are forced to treat the world as a gamble. Even if the universe is deterministic, our ignorance makes it probabilistic.
that is a powerful place to leave it. To our listener, the learner, next time you check your weather app and see 40% chance of rain, remember, that's not the clouds telling you what they're going to do. That is a supercomputer admitting, with mathematical precision, exactly how much it doesn't know.
And trying to help you calculate the maximum expected utility of bringing an umbrella.
Exactly. Thanks for diving in with us. We'll see you on the next one.